Welcome, everyone. Thank you all for standing by, and welcome to our webinar entitled Open Knowledge Network Helps Address Flooding, Water Contamination, and Water Energy Challenges in Ohio. This is a webinar series called Freshwater Science that highlights Ohio's Sea Grant and partnering scientists every month. Every quarter is a different focus, from human health and fish farming to harmful algal blooms and human decision making, bringing applied research to the public on issues that affect our Lake Erie communities. I am Jill Gentis-Badinki from Ohio Sea Grant and Stone Laboratory, and joining me today is Dr. Lilit Yeghiazarian, and I'm sorry, I think Yeghiazarian from the University of Cincinnati. She is the professor of chemical and environmental engineering at the University of Cincinnati. She holds degrees in electrical and industrial engineering from the Polytechnic Institute and the American University of Armenia, as well as her PhD from Cornell. She is a recipient of numerous awards, including the Faculty Early Career Development Program Award from the National Science Foundation, as well as the Ruth L. Kirstein Award from the National Institutes of Health. Her research portfolio covers topics ranging from watershed processes, sustainability, and environmental sensing to porous media and multifunctional materials. We're delighted to have her here to talk about her innovative work. Before we do, just a few things about the webinar itself. During our presentation, all participants will be in a listen-only mode. Afterwards, around 12:20, I'll conduct a question and answer session. If you would like to ask a question during the presentation, please feel free to pull up that chat feature located at the bottom of your screen, and I'll collect and pose your questions out to her at the end of the presentation. As a reminder, this webinar has auto captioning and is being recorded to be posted onto our website for later viewing. Also, we will post a webinar survey in the chat feature toward the end of the half an hour. Please take a few minutes after the webinar to fill out that survey. It will help us continue to bring you great webinars. So without any further delay, I'd like to introduce Dr. Lilit Yeghiazarian, so sorry, who will present Open Knowledge Network Helps Address Flooding, Water Contamination, and Water Energy Challenges in Ohio.
All right. Well, thank you very much, Jill. I would like to thank you and Chris and the folks at the Ohio Sea Grant Office for inviting me to give this webinar. I'm absolutely delighted. I know we have a large audience today and a very diverse audience, so I cannot wait for the Q&A session, and I hope that this conversation will continue long after the webinar is done. As Jill mentioned, we're going to talk about a technology, an AI technology that is called Open Knowledge Networks, and how they help address flooding and water energy challenges. Well, Jill said two critical words. She said applied research. And that is at the crux of what we're trying to do at the University of Cincinnati. We are trying to make research and development that is done in academia together with our stakeholders in a private and public partnership, and make it really applicable to work that people do in the field and in the trenches. And I would love to hear from you any ideas about how you think this could be helpful in your work. And again, I'm looking forward to engaging in this conversation. So the origin of these multiple projects that I put together in a presentation of about 15 minutes in length started with a Sea Grant, with a grant from the Sea Grant Office. And that one was to start looking at flooding problems in Ohio, in particular in Northeast Ohio. And that seed grant really was the beginning of our work that expanded to real-time flooding across the continental US and the capability to address water and energy and also water contamination issues also across the United States. So I think this is a fantastic example of the huge impact that the Ohio Sea Grant makes in awarding giving awards to teams of researchers that partner with people in industry and with people who really do the work in utilities, and to just expand it from the local impact to make a national scale impact. What you see here is a sequence of pictures that describes what happens when a powerful storm hits a city. So we have the power grid that goes out, and because the power is out soon after the sewer pipes are no longer functioning because the pumps have no more power, contaminated water starts flooding the buildings. It affects water quality. People are displaced. Bridges are destroyed. Drinking water facilities have no more power, and our highways become waterways. So we all know that the human and economic losses from flooding are increasing, but we still cannot predict why and how much. And this sequence of pictures kind of highlights a series of cascading failures that hits a city when you have a powerful storm. So on the left, you see a graphic called the urban multiplex, which kind of highlights the idea that a city is really a complex network of networks. We have the surface water, we have dams in navigation, we have the transportation grid, the power grid, civic infrastructure, drinking water infrastructure, storm and wastewater, and groundwater. So we call this urban fabric the urban multiplex. Multiplex is a term for network of networks. And all of these networks are connected functionally and physically, like each and every one of them. The problem is that the data that have been accumulating for decades in each one of these sectors are siloed. And this is the crux of the problem. If the data about a very complex system like a city is not connected, there is absolutely no way in which we could predict what happens when there is a stress on this complex system. So in order to predict the total impact of a flood on a city or a region, the first thing that we need to do is break those silos and connect the data that describe this very complex interconnected world. And that is precisely what this technology called open knowledge networks does. It represents disparate data and connects them. So in a knowledge network, each node is an entity. It can be a person, it can be a building, it can be a power station. And the links between the nodes in this network are really the relationships. So here's a very simple example of a piece of that network that shows a node, which is a power station X, that serves the wastewater treatment plant Y. So imagine that you can actually build out a digital infrastructure, a digital network of data that describes all these entities and the relationships between them. And so we build this kind of network, and now it provides information for real-time response to extreme pressures, such as floods, but it's not limited to floods. It helps in long-term planning and assessing the total impact of flooding on cities. On the left here, you see a very basic drawing of the data architecture. We have here accumulated data about infrastructure and about communities. This data came from open sources, from multiple open sources. You see buildings and roads that came from 3 distinct sources. US EPA provided us with Superfund data, underground fuel storage tanks, and NPDES regulations. The Energy Atlas from the Department of Energy has the energy resources and the power grid, and the Corps of Engineers hosts the National Inventory of Dams. So these data are connected in a knowledge network, and they're coming from completely different sources. But that is the power of the network, when you can represent complex data from disparate sources in a networked way. These data are mostly static because it takes a while to build new infrastructure, so relatively static. But to understand how flooding impacts all of these interconnected infrastructures, we need to super intersect it with dynamic hydrologic data that comes from NOAA and USGS. And finally, we have the capability to connect to other data sources, such as USGS GeoConnex, other knowledge graphs, data commons, US Census, and others. To give you a flavor of how much data is there, here's a heat map at the bottom right of over 150 million critical assets across continental US. These are buildings that include multimodal transportation centers, airports. They include buildings, power stations, power grid. And on the left is a snapshot of in North Carolina, in New Hanover County, showing each dot as an independent resource, an asset such as a building or a power station. And the color represents a different data source. So here you see we have 7 data sources that came together in a coherent digital infrastructure. So now I'm going to do a brief demo. I'm going to switch from my presentation. Just a second. Switch from a presentation, and on the right, you see our real-time flood forecasting system, and I will provide the links at the end so you can play with it. So you see that we have real-time flood warnings at the continental scale. This gets updated every hour and provides flood risk for the next 16 hours. And at the bottom, we have the top 15 live alerts. So it shows that Oswego County, New York, now has 323 structures at risk of flooding. If I click on this, it's going to take us to that map. And we can tell from the pop-up on the left that we have major flooding risk. The total structures at risk are 323. Out of those, 318 are buildings, 5 are underground fuel storage tanks, and 0 power stations. We can zoom in, and we're going to start seeing block groups at some point. Okay, so here is where we are. And you see in this pop-up that you have the block group ID, severity of flooding, and the number of structures at risk. What we've done with this, we also built on top of that an interface where you can interact with the system and ask questions not only about flooding, but also about our water and energy resources. So it's a very simple interface. At the bottom here, there is a place where you can ask a question, or on the left, you can look at sample questions that we have implemented. And these questions were developed within the research group as well as through our communications with our stakeholders, federal agencies, utilities, and cities. And there are questions in different categories. You can ask questions about states, counties, and rivers, dams, coal mines and power plants, hydrology, stream gauges, demographics, economics, health, census tract, PFAS contamination. You can do questions that run some statistics and aggregation questions, etc. So you can pick any one of those, or you can write your own. So I'm just going to demonstrate one. Let's see. Find all coal mines within 1,000 meters of the Ohio River. I'm just going to copy this one, paste here, and let's see what happens. So the system is going to take that question and break it down into simpler questions. Behind all of this is lots and lots of data that were primarily collected by the federal government, quality controlled and quality assessed. So these data are validated on multiple levels. And now we can harvest the data to better understand the environment that we live in. So what it did, it took that question and broke it down into 3 precise tasks. So now it's going to execute these tasks step by step. And it's going to take maybe under a minute, but take a look at what happens. It looks at the Ohio River geometry. And then it starts looking for coal mines within that bounding box of the Ohio River. So this is a condition, a restricting condition. And then it's going to filter to only those that are within a kilometer from the river. On top of that, you can actually see the code that the program will write, and you can use that code. You can download it and play with it. And now it says, I found 394 coal mines within that 1 kilometer box of the Ohio River. Okay. So one of those 300 something mines was within 1 kilometer of the Ohio River. And now it gives you a report that this is the name of the mine, it's Bowser Mine. It's a surface mine. It's in Pennsylvania, Clarion County. It gives you the exact location of that mine and gives you a summary that it's approximately 795 meters from the Ohio River. And the mine produced 5,113 short tons of coal in 2023. So it pulls this information again from a huge amount of data that we can now process. And if you want to look at the map, we can jump to the map. And this is where that coal mine is. We can zoom out and see exactly where it is. And then you can click on this box and download the data that the program produced and use it as much as you like. I'm going to go back to the slides. And again, you're very welcome to play with it. And I would love to hear what you think about it. Okay. So now let's go back to where we started. And we started talking about cascading failures that propagate through the urban multiplex, through the fabric of a modern city. Here's a simulation that we did of a flood around Cincinnati. You recognize the bend of the Ohio River and Highway 50 here, Columbia Parkway. You see here that there is one electrical asset that is flooded. This asset is wet, so it does not produce any power. Well, because we know this area and we know that this water asset is served by the power station that is inundated, we know that the failure of power is going to take out this water asset. Well, this water asset serves 3 hospitals. So these hospitals will not have any drinking water. So even though there is only one asset in this case that is wet, that is inundated, additional assets are losing their services, even though they are not directly impacted. And this is a power of using networked data. You can actually propagate those failures in a digital space, and that would be reflective of what the physical reality is. You see that there are other power assets and water assets that are inundated. So it's not just one cascade. There is multiple cascades that took place because of this event. And the blue polygons here are service areas for water assets. Yellow ones are service areas for power assets. And the red ones are service areas for hospitals. Again, because we have so much data in the background, we can start looking at individual buildings and individual assets. So on the left here, we have a unique ID for every single building, every single power station, every single underground fuel storage tank in the country. We know that this particular building is a kindergarten, and in this scenario, it would lose just the electric service. But there is several schools that lost electric service and the water service. And we can run summary statistics. We found that in this event, 415 buildings will lose at least one service. 43 utilities were the root causes of service failures. So there are 43 distinct cascading failures here. 40 assets were electric, 3 water assets, and 39 medical assets were out. Now, what else can we do with this? Traditionally, when you look at the impact of flooding on a city, the traditional way to calculate the losses is to look at losses due to physical damage to infrastructure. The loss of services is not counted, but we can actually calculate how much money we would lose, how much money the regional economy would lose from, let's say, a 100-year event. And the economic model that we use is called the computable general equilibrium model, and it looks at many, many, many activities. And you have a list of them: agriculture, mining, utilities, construction, manufacturing, wholesale trade, retail, transportation, information, professional services, education, healthcare, arts, recreation, government. So this model captures the impact to the regional economy because people cannot take their kids to school and they have to stay home with them. So this is the level of detail that helps us understand the true impact of a flood on the region or on the city. So this analysis was done for 2 counties, Hamilton County in Cincinnati, in Ohio, and New Hanover in North Carolina. And we were able to calculate using this model the comprehensive loss from a 100-year event. In Hamilton County is $3.5 billion with employment decline of 55,000 and income loss of 1.4 billion. And we have equivalent numbers here for New Hanover. So in conclusion, this approach allows to understand the true impact of a flood on a city. It allows to predict the cascading failures that would take out resources, services, and impact communities. And finally, with that, I would like to acknowledge a large team that has worked on this project for several years. And finally, the information for you guys to play with this system and get in touch with us. So I would like to end this by saying that I would really appreciate feedback on what you think about this capability. We are in the process of finishing our last year of the NSF project. So we would love to hear from you as to how this technology can help you solve your problems. And we would really like to have people adopt it and use it, because this is what it's for. We don't want it in the ivory tower. We want this technology to be used and make really meaningful impact. So with that, thank you very much. And I think we're ready for questions.
All right. Thank you so much. We have gotten some great questions. So let me get started and we'll go through as many as we can. All right. The first question that we have is, and we had a couple people just wanting to clarify when you say at risk. What does that mean? Does that mean the flooding water will reach those structures? So it was just a clarifying question.
So at risk, we do means that just like a weather company will never say you are going to have 5 inches of water at 3 p.m. at your house, we assign probabilities in the back. So at risk of major flooding, it means the probability is pretty high that there is going to be a major flood. And major and moderate and minor are defined by USGS. So major means, you don't even get out of the house. Minor means minor distraction, but you can still get out and drive. And intermediate is something in between. So that's what it means.
Another couple of clarifiers here. One person asked, beyond counties, can you drill down to smaller divisions such as tax parcels?
We can drill down to individual buildings.
Okay.
The
Um,
the interface shows the highest resolution on the interface is block groups, but we're saying how many structures are at risk in each block group, and the data in the back are at individual building level.
okay. Um, when we're talking about wells and mines, can we differentiate between like operational versus abandoned?
Yes, we can.
Okay. Um, Another question we got was who inputs the pressure influence? For example, flooding at 1 foot versus 2 feet versus 3 feet of flood.
There is no one person that inputs it. We collect data from USGS and from NOAA, and then we calculate in the back the risk of to individual assets. And then based on our estimation, we assign the major, minor, and intermediate risk levels. So the data are coming from USGS and NOAA.
Okay. Which approach, um, and they have model, you adopted in the background of this tool to predict the flooding water fate, the hydrology part of this project?
There are actually multiple models. It's a hybrid approach because not a single model you know, has been is known as the most accurate or the best. So we have taken the hybrid approach of using multiple models.
Okay. Um, how can AI make this model more powerful or faster?
I don't think we need to make it faster because it's already very, very fast. So we're forecasting at 150 million locations across the continental US within minutes. Um, so it is already very powerful and it is very fast. And I could say that um, the approach of knowledge networks is what allows this speed and the efficiency. And knowledge networks are on the spectrum of AI. I don't think AI should be interpreted only as large language models. There is a lot more to that, and knowledge networks is one technology tool in the spectrum of AI.
Okay. Um, Sorry, just can the data be used in decision making to reduce flood risk? Like if certain areas might benefit if converted to wetland or other controlled structures?
Yes, the quick answer is yes, you can do that. At the moment, we do not have the capability to do simulations. So we're not running a particular model where we can change the knobs and do particular simulations. But the power of this approach is in the connectivity of assets to one another. So if there is a change in the way things are connected to one another, then it will be automatically reflected.
Okay. Um, a couple of more, just a few more questions. Have you used the model to guide a flood resiliency project for any assets such as WWTP?
Not at the moment, but we are working with several utilities to understand how they can use this particular approach. We have been working in a different project with the Northeast Ohio Regional Sewer District, but that's a slightly different approach that allows for long-term forecasting and predictions.
All right, two more questions. Does it work with lake level rise and ocean storm surges or just river floods?
It works best with river floods at the moment, but we are expanding to incorporate storm surge also.
All right. And what types of industry partners are you seeking?
Um, actually a wide spectrum, from utilities all the way to weather forecasters and anybody in between, municipalities, states,
Okay.
anyone who has assets underground that they want to protect.
And I guess there were a couple of last questions specifically about like the future of this project. Can you talk a little bit about that? What your where this tool will live in the future? What you were hoping to have help with from folks?
Yes,
Um,
excellent question. So this work has been funded by the Ohio Sea Grant and the National Science Foundation. We have a few more months of funding that will support maintenance of this infrastructure online and on the cloud. So you guys can have access to all of this for now. But we have a mandate from the National Science Foundation to sustain this technology moving forward. So we are looking for partners who will work with us to adopt this technology, and it can go beyond of what I showed. It could be boutique solutions to specific problems, so that we can actually pay for our cloud hosting and human resources that are needed to maintain this. So we are looking for stakeholders, clients, and partners.
all right. And you're okay with folks if there's interest to just email you directly?
Yes, please. And you can reach us at these two email addresses that I have on the screen.
All
And
right.
if you want to play with the system, please, by all means, go to that website, data2action.tech, and have a go at it and tell us if you managed to break it, because I would love to know that.
All right. Well, thank you so much. I think we have run out of time. So let me just close with thanking Dr. Yeghiazarian for her willingness to talk to us today about her work. This is really an excellent discussion. I also wanted to remind everyone that the survey URL for this webinar is in the chat feature. So please take a few minutes to fill that out. This webinar series is sponsored by Ohio Sea Grant and will continue next month. Thank you again for your willingness to present today and for all the participants to attending this webinar. We hope that this was beneficial and we hope that you'll join us again in an upcoming webinar. Thank you and have a great afternoon. Thank you again for your willingness to present. This was really great.
Thank you. And thank you, everyone, for joining. Really appreciate it.
Thank you. Thanks again.
Thank you.